One thing we didn't have the opportunity to talk about in class earlier this week was a convenient coordinate system for solving problems with ramps. The standard coordinate system we typically use involves drawing some positive y and x axis, where the positive x-axis is along the horizontal, and horizontal here meaning like horizontal to the surface of the earth, and the vertical axis being at 90 degrees, often vertically straight up. In the case of problems with ramps, I'm going to draw a ramp here that is particularly thin, hopefully for reasons that will be clear soon. Instead of describing the motion of a block as being in exactly the positive x or positive y direction, it's very convenient to describe the motion of this block relative to an axis which is horizontal or parallel to the surface of the ramp and perpendicular to the surface of this ramp. We could call this a lot of things. We could simply call this positive y and this positive x. We could rename it as something else. You could call it a positive something. You could name it just any name you would like, any variable name that you would like. We could also call it something like x prime and positive y prime, if we so chose. That would be off by some angle based on whatever the angle of the ramp is. I just drew a little theta on that ramp. I'm not sure if that's clear in the video or not. The reason that that is convenient is that when we have a ramp of this type, let's say for instance that this ramp is stationary, let's say that it's kind of locked in place. The block on this ramp, if we assume that there's no friction between the block and the ramp, will have a force, a couple of forces exerted on it. There is the weight of this block, which is vertically downward. It's towards the center of the earth, so vertically, in the vertical direction down with respect to the bottom side of this ramp. There is also a normal force which acts on this block, which is perpendicular not to the bottom of the ramp or to the surface of the earth, but perpendicular to the plane or the surface of this ramp. So that points along this direction of this positive y prime that we just drew. If we look at this in terms of the vertical and horizontal components, what we can see is that there is a net force that is acting on this block in the x direction, off to the right here. Or we might even note that that is in also a force, a net force in the positive x prime direction. So the reason that there is a force there due to the fact that this ramp is on some incline, and that clues us in to the fact that this object has some net force along the x prime direction which is greater than 0. It has some positive force along this direction, and therefore we will observe some change in motion. This object will undergo some acceleration. So this is going to be actually equal to this, there is a net force which is greater than 0, and I'll not put the equals here. So we could actually describe that net force in the x prime direction as being equal to the mass times the acceleration in the x prime direction, or something that's along along the surface of this ramp. Here we know a lot of times we'll be able to determine what the magnitude of the force is on this block by the earth, because that's just the weight. That's simply mass times gravity. And this component, so if we want to know the components of this weight in both a coordinate system that is vertical, vertically, or let's say it's perpendicular to the surface of the ramp and also horizontal to the surface of the ramp, that has that describes two components of this force due to the earth acting on the block. So there is a component along the y prime direction and a component along the x prime direction. So this is the weight, and my telephone is ringing. I'm just going to let the answer machine get that, I think. Actually, why don't I stop this quick and we'll come back to this. I'll be right back.